Very good morning, all the participants. And today we have Dr. Dipti Prasad Mukherjee, the speaker for this session. I welcome all of you to the fifth and the final day of this faculty development program. So this session uh, will have the presentation by Dr. Dipti Prasad Mukherjee. Let me give a brief introduction of Dr. Mukherjee. Currently, he is a professor at the Electronics and Communication Science Unit of Indian Statistical Institute, and he is also officiating as the director of the institute. So his presentation will be broadly on machine learning for computer vision applications, highlighting on successful prototypes of imaging applications being developed at ISI Calcutta. So with this brief introduction, I request Dr. Mukherjee to continue his presentation.
Okay, good morning and thank you, Professor Suprabha Patnaik. Am I audible? First of all, I think this is the question. First
Yes, sir.
question.
Yes, sir. You are audible.
Okay. Um, okay. So yes, my presentation will be on imaging applications and and the kind of use of machine learning that we are exploring at different levels. So during my presentation, my plan is to give you first a basic introductory overview, which probably you already know, but just to make sure that we are on the same page, about 15-20 minutes of presentation on basics. This will be followed by introduction of different imaging applications. And then finally, depending on how much time we have, I understand that this session will be up to 11 o'clock. So depending on the time we have, I'll go and zero into any one particular application and try to look at the application in further detail. So that is the overall plan. And in between, if you have any question, just just say a question. I'll stop there and we'll try to understand the disconnect between you and me. Okay. With this, let's proceed to the presentations. Okay, so in a single slide, if I have to say the objective of the imaging applications, it is simply this, that here is a flower image. We all recognize it. The question is, can a computer infer that? So can we develop an algorithm to understand the content of the image? If you look at any standard computer vision textbook, you will see there are three distinct steps. We call it pipelines. There is at the initial level, it's a low-level processing, and we can call that as low-level image processing, because what the system is going to get is low-level information, pixel information, and then it processes that low-level information, might include filtering, enhancement, or something similar operations. Then the information comes to the mid-level information extraction process. One of the very popular mid-level information extraction is segmentation, which means you take the segment out and then finally you infer the content of the segment, what the segment is, and that's what we call as the high-level information processing. And traditionally, when we say that we apply machine learning or AI techniques, it is basically in between these mid-level and high-level, as you can see on the slide. That is where precisely we bring in the concepts of machine learning. However, having said that, I also understand and acknowledge that in today's paradigm, machine learning is not only compartmentalized in between these mid-level and high-level process. It is now encompassing the entire pipeline. So be it low level, be it mid-level, be it high level, almost at every level, we can have a machine learning technique. We can have one integrated machine learning system, for example, the deep learning systems. And therefore the slide is kind of archaic, and machine learning applications are sort of all encompassing in this field. Essentially, by machine learning, I would like to focus on two aspects, and that is probably the 90% of the problems that we look at. And I'm going to give you, I think in today's talk, I only concentrated on the engineering applications. Even if you look at medical applications, medical imaging applications, they're essentially two parts: clustering and classification. One is unsupervised, clustering is unsupervised, whereas classification is supervised learning. So just to give you a very brief introduction on that, I have a set of data points. So assuming this is a group of persons between 19 to 26 years, and I just say that you clustered the data. I also say that you clustered them into two different age groups. So you apply a clustering technique. So can any of you name any clustering algorithm?
K-means clustering.
K-means clustering. Yes, that's one of the widely used and widely abused clustering algorithm. But I would like to take attention to the fact that that the number of clusters are given in the problem. Can you name an algorithm where the number of clusters are not given?
Partitional clustering.
What is that? Can you repeat, please?
Partitional clustering.
Additional.
Partition.
Partition, yes, but you don't know the number of partition.
Yes.
Well, we'll see. We'll look into the problem. But please keep your attention on this term too, because that's very important. In clustering, you might have a priori knowledge, but in all practical field and practical sense, probably you do not have the idea of number of clusters. The next important problem in machine learning is, of course, classification. And you know so many of the classification algorithms. Again, can you name any one of the classification algorithm? Anyone?
SVM.
SVM is a very good example. In fact, yeah. So if you can look at these, if you can look at the slides, I'm sure the slides are available. Slides, you can see the slides, right? So you have two classes. Maybe one class have flower dahlia, the other class is the flower chrysanthemum. So you have these blue dots and you have these I don't know, close to orange dots. And what important observation in these classification is that you have these black line or black separators which divides these blue dots or separates the blue dots from the orange dots, right? And what is the difference between these classification approach with respect to the clustering? Anyone can highlight the difference? Hello? Can anyone highlight the difference?
We are linearly classify this two different kinds of dots.
So yes, it is linearly. So this line, the black straight line actually linearly divides this, but essentially classification is a supervised process.
Yes.
See, when I'm saying there are two clusters, here are also two clusters, class 1 and class 2. But the major difference is the class 1 has a label. I know what the class 1 is, and the class 1 is flower dahlia. Whereas the class 2, which are the orange dots, is the class chrysanthemum. So you add a label, you add a name to the class, which were not available during the clustering process. So that's the basic difference, and that's why we call this as a supervised clustering process. Supervised clustering process, where you have clusters, but the clusters also have name. There is a teacher, and the teacher is telling you that here is a class 1 and its name is cat, and here is another cluster whose name is dog. And there is a separator which differentiates cat from dog. So then what is the challenge in the classification? To understand the challenge, look at that sort of greenish rectangle at the top with a question mark. Can anyone signify why I put a question mark there?
Where should be the separating plane should lie so the both the class can be classified perfectly.
Yeah, but with respect to that rectangle where there is a question mark, so what it tells us is that
Which
these
classifier is required to be used? That may be the question.
yeah, the
Which
question, let me
classifier is to be used?
yes,
Position of a line. Position of a line.
position of
Like
a line is very important, yes, but position of line separates the dahlia class from the chrysanthemum class. Okay, but what this green rectangle at the top is an unknown object. It's an unknown flower. So the question is, to which it belongs to? Is it belong to class 1 or it belongs to class 2? So is it a dahlia flower or is it a chrysanthemum flower? So that question we need to answer, and that is the challenge of the classification. Am I clear on this point?
Yes, yes, sir.
Yeah. So this particular thing we always call as a query or a test image or a test object. And so the test object, the objective of classification is to assign a label or assign a class to the test object, to the unknown object. Okay, and that's how it gets differentiated from the clustering process. Whatever you do, you essentially actually look at the features of the objects. So in the last problem, if you go back, uh, page up. No, how do I go back? Oops. Sorry, previous. So if you go back here, I have the dahlia class. Now, how these blue dots represent dahlia? Because dahlia has certain features, certain characteristics by which these blue dots will be found out. Similarly, the flower chrysanthemum has certain features, and those features are the attributes or the properties of these orange dots. So therefore, when I differentiate or draw this separator line, black separator line, I look at those features, those characteristics, and based on that, differentiates the blue from the orange. That's what is been described here. So if you consider that clustering problem, I say that there are groups of there is a group of persons. Can you divide them into two groups? How do you do? The immediate question is, how do you divide them? Well, you might divide them based on their height. You might divide them based on their age. You might divide them based on their income. You might divide them based on their weight. So all these are their features, and based on the features, you separate them into the number of clusters given to you. Not necessarily you have to use only one features at a time. You can use two features. For example, in this example, I have used height and age, and therefore these points are representations of these persons in a height and age space. Is this understandable?
Yes, sir.
So what these green dots represent? So what?
Feature points in 2 dimensions.
Okay, so each feature point. So how many feature points should be there then?
Number.
There are
As
two
per the number
features.
of samples.
Yeah. How many feature points should be there?
Based on the number of samples.
Exactly. So if there are n number of data points, then there will be n number of such feature points. And for visualization, we have used 2-dimensional space. You could also use 3-dimensional space. But in practical real-life applications today, you are looking at 100,000 such feature spaces. So really the problem is huge. The problem is complex. And it's not, visualization itself is a big research problem. How do you visualize these data points or sample points in the feature space? That itself is a very important research area. Okay. So far, is it fine? So far, any question?
No, sir, we can do.
Yeah. Okay. So we'll be working with images. So therefore, just to give you, I think all of you know what a digital image is. I don't want to, go into the details, but just to give a brief introduction, an image is always a matrix. It could be 2D image, so 2D matrix. And then if it is a 3D image, then it would be 3D array. So on the top, you will see a matrix where each of these square blocks is a pixel, and these pixels are connected with each other in 4 connectivity or 8 connectivity. And if it is a 3D pixels, what we call these 3D pixels, any idea? There is a specific name. Anyone?
Planes, they belong to a particular plane.
No, so it's an image. I hope you understand what a digital image is, right? It's a collection of pixels. But an image could be 3-dimension also. And by 3-dimension, I mean it has got an x-axis, y-axis, and z-axis. And the z-axis could be a time axis. Z-axis could be, the dimension of the world. For example, CT scan image. When a CT scan is taken for a patient, for a given organ, you actually take slices along the z-axis, and that forms a 3-dimensional image. And we call each of these small blocks in 3D as voxel, volume pixel, voxel. So these voxels are connected with each other in either 6 connectivity, 18 connectivity, or 26 connectivity. So I am not going into details of the connectivity issues, but these are some basic informations. Maybe you can go back to the books and understand. And since we will be working with the pixels, I thought that just one slide may give you the basic introduction of an image, either in 2 dimension or in 3 dimension. So if I go back to that basic problem, that question I start with, that here is a dahlia flower maybe, and I would like to recognize this to be a flower. I would like to write a computer program to understand that this is dahlia flower. What should I do? Well, the step one is, it's an image matrix. So here is a matrix you can see, which has got how many rows? You have So you have 1, 2, 3, 4, 5 rows, 1, 2, 3, 4, 5 columns. So it's a 5 row by 5 column matrix. And these numbers represents the pixel values. By the way, what this number represents?
Intensity of a pixel?
Exactly. These are the intensity of pixels. So what would be the minimum value and the maximum value of these pixels? This intensity value?
Minimum is 3, maximum is 12.
No, the minimum should be 0.
And 256.
255 would be the maximum.
255.
Yeah. So the reason is reason is that for each pixel value I can assign what? How many bits? Since the maximum value it can take is 255, so I can assign 8 bits to each pixel. Correct. Yes. Yeah. Okay. Now this is just a toy example to understand the problem. I'll look at this problem into 2 parts. One is I'll take this central red part of the dahlia flower out, and then which is on the top right hand side, you'll see that red portion taken out, and whatever the remaining portions are represented using a black, and we call these as a segment, as pieces. So we are familiar with the term segment, right? Now the question is, how can I take this segment out? How can I outline this red segment? And here is a technique that I'm showing by which we can take this red segment out. Is that that makes sense? Okay, so if we go to the first slide, if you remember that we have that low-level processing, then I have mid-level processing, and then I have a high-level processing. And by the mid-level processing, I meant that you take a certain portion of the image and call that as one segment, and then you divide the image into different segments, pieces. And that's what is the mid-level processing. And once you have that segment out, you try to name the segment. What is this segment? Is this segment dahlia? Is this segment rose? Is this segment background? Is this segment leaves? So try to answer those questions. Right? So these are these 2 distinct steps that we are going to follow for this problem. Am I sort of clear?
Yes, sir.
Okay. Okay. If you look at the screen, any question? Okay. So let's look at that. There are small green bars. It's kind of a graph that I have drawn on the right hand side. Can anyone tell me what this graph represents?
Histogram.
Histogram. So I am assuming that we have fairly good idea about the histogram. So here, this matrix, which has got 5 rows and 5 columns, I have actually taken these numbers, the numbers of the pixel values, like 5, 8, 12, 10, etc. And I just counted the number of 5, 8, 12, 10 and plotted the histogram on the right hand side. Can any one of you tell me that why I need to draw a histogram?
To understand the intensity population of a particular intensity.
Correct. And by looking at the histogram, can you tell me which pixel value is occurred maximum times in the matrix?
8 pixel
8.
value.
8.
8. And how many 8s are there?
7.
7.
Good. Very good. 7 8s are there. But by looking at the histogram, can any one of you tell me what information it is giving me?
Eight is appearing maximum number of times and 9 is appearing only once.
Frequency of numbers.
Frequency of number, that is correct, yes. And 8 is appearing maximum number of times, 9. In fact, 11 has occurred never, right? But by looking at the graph, any idea what information it is conveying?
Class intervals.
Class what? Class
Intervals.
Class intervals. Yes, very good. What kind of class intervals you can see? Can you tell me how many classes are there by looking at the histogram?
2 classes.
How do you know that? How do you know that? No, you are correct. You are correct. But how do you get a feel that there are 2 classes? If you look at the histogram carefully, there is a peak at 8.
Peak.
Right?
Peak.
And what is the next peak? There is a peak at 8. What is the next peak?
Peak at 5.
5.
Peak at 5.
5. Very good. Excellent. So I can see, and you see all other numbers are mostly 2 and 1. So I can see that there are mainly 2 groups of pixels, 2 clusters of pixels. One cluster is sort of peaking at 5. The other clusters is sort of peaking at 8. So I can now fairly get a good idea of how many clusters are there. And how many clusters are there? Tell me how many clusters are there?
8 clusters.
No, there are 2 clusters because there are mainly 2 peaks. One is at 8 and one is at 5. Most likely. See, number of pixels having pixel value 8 is 7 and number of pixels having pixel value 5 is 4. So it's most likely that there are 2 groups and others are sort of noises or background. And if you look at this flower image, just look at the flower image and intuitively tell me how many clusters are there.
2. Background and foreground. Flower.
Exactly, yes. See, exactly, histogram is giving me that information. So if you just look at the picture and from our sort of intelligence, we clearly know that there are 2 clusters. One is the central red part and other is the background part. And if you would like to find it out automatically, maybe histogram is one of the very important tools by which you can differentiate between the red and the black backgrounds. So if I just pick all the 8 pixels and pixel value close to 8 and draw a boundary in the image, then I will get the red segment out and whatever remaining will be my background, which is sort of peaked near 5. Is that understandable?
Yes, sir.
So that's what is all about. So these are typically called the bimodal histogram. Not necessarily life is always bimodal. If it is bimodal, then it's good. But many places there could be trimodal, many modes. Finding out modes will be difficult. And there are many mathematical and statistical techniques to actually discover the modes. But for our understanding, and for sort of a toy example, here is an example of bimodal histogram, where the first mode, right, first peak actually represents the background regions, which is closer to 0. And what are the value of these peak that we have seen so far? Any idea, roughly? If we remember the last slide, what was the value of the first peak?
5 and 8.
Yeah, around 5. The first peak was around 5, and the next peak was around 8.
8.
Yeah, that was just a toy example that we explored. Okay, so once we have that two segments out, so I hope that you have now understood that we have that red and the black, these two segments separated. Is everybody okay with that separation?
Yes, sir.
Okay, so if we have that ready, then my next immediate question is, I'll look at the segments and I'll ask the question, is it rose? Is it chrysanthemum? Is it dahlia? And what should we do for that?
Sir, the green leaves will not be considered here.
No, in this case, I am assuming it's a toy example. I'm saying all leaves and everything are background. Because I just said that it's a 2-class problem. If you consider that to be 3-class problem, then probably leaf will come out as a separate class. And then the black portion other than the leaf will be the 3rd class. Right? Is this clear? So it depends on my definition. I clubbed one peak to be at 8 and all other things to be another class. And that's what is the black part, the background, which you can see on the right hand side of your screen. But if you say that I would like to discover 3 modes, then probably leaf will come as a separate class, and the black portions that is there in the image can come out to be the 3rd class. Okay, to label the classes, you remember that supervised clustering problem, supervised, that you now have to put a name. So what you do is you now calculate features of these objects. And what features we can calculate? We can calculate area, we can calculate centroid, we can calculate orientation, we can calculate circularity. How circular the object is. What is the area of that segment, the red portion? What is how is it tilted towards a particular angle? So all these we can actually numerically calculate, because these are all pixels or dots. And if you remember that slide of 4-8 connectivity or 6-18-26 connectivity, by that I can calculate the number of pixels, its perimeter, its area, and all these geometric properties. And these numbers like 39, 3,4, -10, all these gives me these feature values. Just like that slide where we said that here is a group of people and I would like to differentiate the group of people based on the age, based on the height, based on the weight, something like that. Now I have certain pictures of flowers on the left hand side of the screen. Can any one of you have any idea about why I put those images on the left hand side?
These are the number of class in which I want to separate out my data.
These are the number of, these are the classes, yes. These are the possible classes actually, right? These are the possible classes to which I would like to label this red part, right? So it's sort of human teaching, human learning process. So if a kid is trained, if a kid is trained to learn what is a cat, what is a dog, and what is a cow, so I'm assuming that the kid has built a model mentally about the cat, about the dog, and about the cow. And now an unknown animal comes. So the kid, maybe, I don't know, maybe the kid is going to map that unknown animal to any one of these three classes. Because he or she has the model of cat, dog, and cow ready, he or she is going to do what? Any intuitive explanation? So the kid is going to compare that unknown animal with his or her model of cat, with his or her model of cow, his or her model of dog. And the one which is closest, he or she is going to map that unknown animal to that particular class, either cat or dog or cow. Isn't it? Isn't that could be a logical conclusion?
Yes, sir. Yes, sir.
Yeah. So exactly that process is what I'm replicating here. Assume my algorithm already knows these three flowers. Maybe flower A, flower B, flower C. And I have to compare this flower A, B, C with this red segment and see whether the red segment is closest to flower A, to flower B, or flower C. The one which is closest, I will name them as belonging to that class. So now, let's give 15 seconds and then let me ask this question. How do you think it is possible? With this understanding so far, how this is possible? Any volunteer? So if you look at that red segment, and I would like to compare the red segment with these three flowers, how is it possible to compare these segments with these three flowers? Yes.
Only by shape only. Shape only.
By what?
By shape only. Otherwise,
By
By-
area.
By extracting the features from the
By
shape.
extracting the features, exactly. Very good. So then let's organize the thoughts. So how do you go about? What is step one? What would be the step one?
Segmentation is the first step. After doing the segmentation, we can come to
Segmentation of
the
what?
area centroid. Huh?
Segmentation of what?
Sample image given to
Which
the
which sample images? So these three sample images, right? Let's call them flower 1, flower 2, flower 3. Okay? And then you segment them. And then you find out all the features of flower 1, flower 2, flower 3. And what are the features? What are the features?
area orientation.
Yes, area, see any features. I mean, you can come up with your own features as well, different features. And once you calculate them, you store them in your database, right? You have hundreds of such manual segmentation done. You have already done it. Yes? And then an unknown flower will come, and on your right hand side on the screen you have these dahlia flower, unknown to the computer algorithm. Then you do what? Once this unknown image comes,
Comparing it with the already stored features.
exactly. So how do you compare? So before comparing, you also do the segmentation on these unknown image.
Yes, yes.
And how do you do the segmentation? You can draw that histogram. You can
Same
find out.
way. Yes.
Yeah,
Same
same,
way.
exactly the same way. And once you have those segments, then again, for the unknown piece, you find out the same features, right? And then you do what?
Calculate the feature distance.
Exactly. Very good. Excellent. Feature distance. So you compare those features. And by comparing, we mean the finding out the distances between the area of flower 1 and the area of the unknown. Find out the distance between the centroid of flower 1 and the centroid of the flower of the unknown. So like that, you calculate the distances. So for 3 flowers in your database, flower 1, flower 2, flower 3, how many total distances you should be able to calculate?
Oh,
Three distances for three
Well,
flowers with the taste flower.
oh, with the test flowers, yes. So for the test flower, you will have 4 features, and you already have 4 features calculated, right? Comparing these 4 with these 4, you get 1 distance. So for each flower, flower 1, you have 1 distance value. Flower 2, you have 1 distance value, and flower 3, you have 1 distance value. And this distance value actually takes care of the number of features. In my toy example, there are 4 features. You might have 400 different features. And then how do you assign the name to this unknown flower?
This distance will be compared to a threshold. Wherever the threshold is minimum, it will be assigned to that class.
Exactly. Perfect. So compare the distance, calculate the distance based on the features, assign the class level based on the minimum distance. Yes. Very good. And that's what we did in the next slide. My question here is now, can we recognize the object? Yes, we can recognize the object. For the object, in this case, the question object means the unknown. I calculate feature 1, feature 2, feature 3, feature 4 up to feature n. And in the model, which is already stored, I have hundreds of such flowers. And we call them, model 1, feature 1, model 1, feature 2, model 1, feature n, model 2, feature 1, etc., etc. And then you find out the distance between the features and the model features. Wherever the distance is minimum, you recognize based on that minimum distance. Hopefully this is clear.
Sir, this process is completely done after segmentation, right?
Yes. I mean, because feature calculation has to be done on the segments, isn't it? Because unless you have the segment, you don't know what is the flower area. You don't know what is the perimeter of the flower. You don't know how circular the flower is. So all these properties you can calculate only when you have the segment with you.
Sir, just one question.
Yeah.
How to decide then the segmentation algorithm? How to conclude upon that, algorithm selection for the
Okay.
segmentation?
See, there are hundreds and thousands of segmentation algorithms. The one that I described as a toy example is the histogram-based segmentation. So I will look at the pixel values. I will draw a histogram of the pixel values, and histogram will show me the peaks. You remember the peaks? How many peaks were there? 2 peaks were there in my toy example. and these two peaks represents two clusters. And naturally, if you look at the image, there are two clusters. One is that reddish flower part, and the green and the blackish background part. So that is a very toy, simple segmentation algorithm that I have just introduced. But you can come up with many sophisticated clustering algorithms. You can use k-means algorithms. You can use fuzzy C-means algorithms, and etc. etc. Is this my clear to answer to your question?
Yes, sir.
So one thing, sir, actually
Yeah.
in terms of coding, while implementing actually this in algorithmically or in
Yes.
terms of coding, so
Yes.
how to actually get this centroid area? I've seen it actually in many papers, but far as implementation is concerned, any
Yeah.
suggestion
Yeah.
how to
Yeah. I
do?
mean, the magic is there are there are magic interpreters
Centroid
available. Something
area.
like I'll tell you something like, have you heard MATLAB, Python?
Yes, it is there, but inbuilt
Everything.
functions are there.
What is that? All these
Inbuilt
commands,
functions available.
all everything, yes. And so, if
Okay,
you do
okay.
not want to understand anything, then use MATLAB and Python. They will calculate all these features for you. Right?
Okay, okay.
Typically, MATLAB could calculate 60 or 70 features. You give a segment, it calculates the features. There is a command called region props. Region
Okay. Thank you.
properties. Similarly,
Okay, thank
Python
you.
has that command. But if I assume that you are a teacher just like me, then please do not use those commands, and try to understand how the area is calculated, how the perimeter is calculated, and so any standard basic textbook will explain that to you. It is simply like in a graph paper. Think this image as a graph paper. So in the graph paper, if you draw a segment, and
Yes,
then
sir.
how do you calculate the area of that segment in a graph paper? Exactly the same process you can replicate in a computer program.
Yes.
Use two for loops, and then find out the area of the pixels which are black or which are red, and then eliminate all the pixels which are not red or which are white. So just count the number of pixels, you get the area. Just count the number of black pixels, you get the area of the black segment. Just count the number of pixels having color red, then you find out the area of the red segment. So that is how you proceed. So all these
Yes.
algorithms are known and simple. So please explore it from the basics. And my suggestion is not to use MATLAB or Python to use to find out these basic routines. Well, you can use it, first understand and then use it.
Yes, sir. Yes. Thank
Yeah.
you, sir.
Yeah. Okay. So I think I'm very slow. Not only slow, it's extremely slow. So I probably won't be able to cover much of what I thought about. But more important is whatever I'm saying, whether it's clear or not. If you have any more questions on this up to this, please feel free to ask. Okay. So next important question, therefore, is how do we calculate the distance? So we now know the motivation of distance. The motivation of distance is you are comparing the features of unknown segment with features of known segments. Known segments are already stored, so you already have the feature values of the known segments. You pick up the unknown segment, calculate the same features, and find out the distance. Okay. The most popular distance calculation is, obviously, we all know from our school days, is the Euclidean distance. And the example on the screen actually shows you that how the unknown is leveled. Now, Can you see this graph x1 and x2?
Yes, sir.
What is this x1 and x2 represents?
Features.
That's features, exactly. And what is this prototype 1 and prototype 2 represent?
Sample.
Like?
That is the train samples.
Yes. So maybe the red one is flower chrysanthemum and the green one is the flower rose, right? And then this unknown, which is the black dot, has to be assigned to any one of them. So I can simply find out the Euclidean distance with respect to green and with respect to the red. And I know that x1 minus x2 whole square plus y1 minus y2 whole square of square root gives me the Euclidean distance value. And the one which is the minimum is that prototype is assigned to the unknown. Is this clear?
Yes, sir.
Yeah. But the problem comes if you actually look at the training samples, the stored samples. Can you see the stored, the representations of prototype 1 and prototype 2 now?
Yes.
Can you look at these example and look at this example? What is the difference? What is this ellipse, green ellipse or pink circle represents? What is that? See, this is very interesting and complicated problem. I mean, we are gradually going towards a very complicated scenario. See, let's assume
Distribution of samples.
What is that?
Distribution of the samples.
Distribution of the samples, exactly. Yes. So if this red dot actually represents flower rose, then the rose, there are many kinds of rose. And so obviously the area of roses and the centroids of roses, perimeters of roses, orientations of all these are going to vary and vary quite a bit. And these variations, the distribution of these variations will look like this circle. And that's how you get this distribution. Similarly, the one, let's say this green one is the chrysanthemum, and this distribution looks like this huge ellipsoid. Yes. So now, if you compare this to the previous slide, by distance, probably unknown is much closer to the red compared to the green in the Euclidean distance sense. Can everyone follow me?
Yes, sir.
But the moment if you look at the real scenario here, looking at the distributions, you will see that the black dot is much closer to the green one because of the spread of the variations of the distributions. So if there is a less variation in rose and more variations in chrysanthemum, then the unknown may be mapped to the chrysanthemum compared to the red ones. And this actually brings in new sort of definitions of the distances, and our traditional idea of Euclidean distance might not work in such a complicated scenario. And one of the very popular distance considering these kind of distributions is Mahalanobis distance, and Mahalanobis distance is a weighted Euclidean distribution which can take care of such distribution of the samples, of the training samples. Now, this is just to give you an idea. It's again a very important research topic, and so blindly using a distance may not work, even though in most of the cases we use blindly these distances, and in 99% cases probably we'll be using Euclidean distances, and maybe out of that 60% cases we'll fail, and we fail because we have not properly taken care of the distribution of the training samples. The reason I am mentioning these, that there are research directions, there are important developments, and people should be able to explore other kind of distances and properties as well. Even more difficult is a scenario like that. See, if you consider I name this as a distance on the manifold, right? So if you are considering Euclidean distance, you are actually looking at a crow distance between 2 points, the point A and point B. You are finding out the distances between A and B. And your assumption is that there is a plane passing through A and B. Okay? But there may not be a plane. There may be a nonlinear surface. And this manifold is that nonlinear surface. See? So here is a point X. Can you see the point X on the manifold? Hello? Can you see a point? Can you see a point Y on the manifold?
Yes, sir.
Yeah. So what you can do is you can actually find out the Euclidean distance between X and Y. However, maybe the data is distributed in such a way, sort of a kind of a shoe surface here. Then your distance may be better calculated if you follow along the surface of the shoe. So you actually find out the distance on the manifold, not along the crow distance, not along the bird distance. So the bird is assumed to fly from point A to point B in a minimum distance fashion. But maybe your distance calculation could be completely wrong if you follow that. And that's what happens in many cases. So when a machine learning algorithm fails, never blame that on the machine learning. The problem lies with your feature calculation. The problem lies with your distance calculation. So a k-means can never be wrong. A fuzzy c-means can never be wrong. They are always right. But what is wrong is your assumption of features, your assumption of distance. Maybe the kind of distance you have used may not be suitable for that particular application. Maybe the feature design is an art, it's not a science. So should we take area or should we take centroid? Should we take height or should we take income as a feature? It all depends on a particular application. It depends on you. So these are art, not science. Therefore, the quality of the work, quality of the algorithm, performance will certainly depend on these sort of issues. My objective of bringing in these ideas is to introduce you to these challenges. Not necessarily we are looking at all aspects of it, and in fact it all brings to a whole semester course, but just to give you some ideas, pointers, that where it can go wrong. Is this understandable so far?
Yes, sir.
Hello, sir.
Yeah.
So how to know the manifold that you said? Suppose we have a feature vector,
Correct.
another feature vector,
Correct.
X and
All
Y.
the
So
distributions
how
are
do
there.
you know that?
So it's very difficult.
Based on the distribution.
Based on the distribution. So first
Actually,
2 ways. Yeah.
okay. Now actually you said us if it is the spread is more, then Mahalanobis distance will be better, and if the spread is less, then Euclidean distance.
No. I cannot. No, you cannot just make a call like that. See, you have to impose certain distributions. For example, you say that the features are normally distributed. Normal distribution, or you take a Gaussian distribution, exponential distribution, beta distribution, gamma distributions. So you normally actually assume certain distribution, right? Now immediate question comes, okay, if there are two features, you should be able to see that. If there are three features in three-dimensional space, you should be able to see that. What happens if it is more than 3 dimension? You won't be able to see that. There is no way you can visualize it, isn't it? So really, it's a very challenging problem. Now there are certain techniques which you can certainly employ. For example, I don't know, I'm digressing a little bit, but have you heard of the technique called principal component analysis?
Yes.
Yeah. So
Principle. Yes, sir.
or factor analysis. There are many such analyses. What it can do, let's say you have 1,000 features. Certainly you have no idea how the features are distributed because you cannot visualize them. Then you can do those analysis to find out the most important features. So maybe you picked up first 2 or 3 important features out of them. And then look at the distributions of those first 2 or 3 important features. And that you can certainly do because you have 2-dimensional or 3-dimensional visualization techniques known to you. By looking at those distributions, you select either a normal distribution or a gamma distribution or a beta distribution, so on and so forth. And then you have a fairly good idea about the manifold. Then you decide whether you go along the manifold or you take simply Euclidean distance or you take a Mahalanobis distance. Am I sort of clear on this point?
Yes, sir. Actually, based on the distribution, we will select which type of distance measure should be suitable for the application.
Correct. There is even another way to do that, is that even if assuming that these distributions are completely nonlinear, then any nonlinear function you should be able to approximate with piecewise linear functions. Piecewise linear function. So think of you are drawing a circle, and what you can do is you can divide the circle into very small linear segments, small lines. You join small lines and then form a circle. Assuming you are drawing a freehand curve, third degree polynomial or fifth degree polynomial, but you can certainly approximate them with small lines. Take small lines, connect them one after the other, and you can approximate that to be a manifold. So even if these unknown manifold that is on the screen, you can divide them into small linear segments and then apply for the small linear segments Euclidean distance. So instead of finding out Euclidean distance between x and y, you have thousands of Euclidean distances between small steps along the manifold. Does that make sense?
Yes, sir.
Or I think I'm making things complicated, but anyway, this class is all about to have an idea about the challenges. If you are interested, you have to go back to the books and basics and explore a little more.
Yes, sir.
Okay. So just to sum up, these are the challenges. Yes, distance calculation is a challenge. Features is a challenge. Initialization is challenge. See, the question I had asked earlier, initialization is how many clusters? So by looking at the histogram, I said, well, there are 2 clusters, 2 red stars. But someone will say, no, there are 3 clusters. Someone has actually pointed out that flower could be a cluster. So like that, so these I am calling as an initialization problem. How many clusters to start with? Do we really know the number of clusters? What happens in a problem where I don't know whether there is clusters or not? Finally, the memberships. Membership is also a very important challenge. When I'm saying that this is a flower and this flower is a rose flower, I'm saying that these unknown segment, I'm 100% sure that this unknown segment belongs to red flower. But it might happen that you have your model. In your model you have three kind of flowers: chrysanthemum, rose, and maybe dahlia. But the unknown segment may not belong to any one of them, a completely unknown. In the terms of statistics, these are called the outlier. So it could be completely out of these three. So you have zero membership value. And that's a very important and very challenging problem. And nowadays, when we are actually practically working with industrial image processing problems, we can often see such scenarios, and we call that as an outlier detection problem. Even you can get a flower which is not exactly like a rose, not exactly like a chrysanthemum. So maybe it is 60% or 70% rose and 30% looks like a chrysanthemum. So you have a membership which is fuzzy. You have a membership which is not very precise. And that also is a challenge, in fact, research challenge in this domain of the problem. So to sum up with the discussion so far, these are four areas where we should actually look at in a little bit detail. Okay, any question? Okay, so naturally, if we look at this initialization problem, the first question that comes into our mind is that what if we do not know the number of clusters, right? So a company is trying to sell a product. The first question that comes to the company's mind is that, will there be a customer for this product? How do I know? Well, you do a market survey. And what is market survey? You kind of get certain answers to certain questions. I can call them as features. So by looking at the features, you discover whether there are at least a cluster which represents a possible set of buyers. So we do not know. We do not know whether the cluster exists or not. We have to discover whether there is a cluster. We cannot a priori say that there exists a cluster which are potential buyers of this product. Is this clear, this question or challenge? Hello? Hello?
Yes, sir, continue.
Yeah. Okay. So one of the very popular technique in that direction is the density-based clustering. These are also known as the DB scan algorithm, density-based scanning. So what you can do is you can look at the distribution of the points. What do you mean by points? Points are those samples. And then starting from a given sample, you find out a neighborhood and see how many neighbors are there within that neighborhood. So for example, here we said there is an epsilon neighborhood, and within the epsilon neighborhood, how many such points are there? So remember, these points now actually represents features. So let's assume it's a two-dimensional feature space. These are the customers, right? And the two axes are, one axis could be their annual income, and the other axis could be their annual expenditure. So let's say by some survey, we have found out their income and expenditure, and we have plotted all those points against the income feature and the expenditure feature space. Therefore, given the point, see how many points are closer to a particular point. And we should be able to look at, starting from a point, let's call that point as a core point, we'll try to see how many points are in its neighborhood. For example, there are 4 points in the neighborhood of the core, and then consider each of those neighbors as their next core points, find out the neighbors, and continue this process, and then form one big cluster consisting of 3 such neighborhoods, right? And the one yellow at the top becomes completely separate, and this becomes an outlier, because within epsilon neighborhood, he or she does not have any neighbor. So this is considered as the outlier, whereas the rest of these points are considered as one cluster. So I can discover in this data set through densities clustering that there are 2 clusters. One cluster consists of 1, 2, 3, 4, 5, 6, 7, 8 points, and the other class consists of only 1 point, the yellow one. So these are called density reachability problem. I would request you to look at these algorithms. If you are working on a problem similar to this, study this algorithm. There are many tutorials on the web, even Wikipedia pages are there, where you can discover the density of the cluster points, the pixels. So you start from a core point, discover its neighbors, find out the neighbors of the next core point, find out the next neighbor or the furthest neighbor, find out its neighbor, and continue this process. And if there is a connection, you can establish. Till the connection goes, you can draw a large cluster consisting of all those points. And you can automatically discover how many such clusters are there. So, any question? Is the objective clear? Yes.
Yes, sir. So, how is this similar to the knowledge graph?
Well, that's almost similar technique, yes. But the knowledge graph will have some other attributes. So it has got a graph will have it could be directed graph, it could be undirected graph, there could be cycles, right? So all those properties can be ascribed to a knowledge graph, which is not ascribed to the DB scan problem, because in this simple clustering we do not need such informations. So knowledge graph or aspect graphs has some more additional, we call it semantic properties, some meaningful properties. Those meaningful properties are absent in these kind of DB scan algorithms. This is much more straightforward algorithm.
Okay.
Much more lightweight algorithm. Start from a point.
Okay, got that.
Start from a point, go on discovering its the neighbors. Okay.
Okay.
Yeah.
Yeah, thank you, sir.
Yeah. So that's kind of final results probably we will get of clustering. We have already seen the classification problem. So one of the most important question, which hyperplane to choose? So you know that we have discussed this black line separating the blue and the orange dots as the separators. We can call that as a hyperplane. Why I am calling that as a hyperplane?
Because, sir, it may not be necessary that it will be in a 2-dimensional only. If we could use kernel, it will go to some other dimension also.
N-dimensional, much more higher than the 3-dimensional space. Yes, and that's why it's a hyperplane. So the immediate question comes, I mean, I could actually draw multiple such hyperplanes. So is there any way to find out the best hyperplane out of them?
Yes, sir. To see the maximum margins, like between the two features.
Right, absolutely correct. So it's not only maximum margin, we have to also see minimum misclassification, right? In my examples here, I can clearly see that the classes are well separated, which may not be the case in real life. So maybe one red dot would be on the other side of the hyperplane. Maybe one black dot could be on the other side of the hyperplane. So that's a misclassification. So you draw that hyperplane, yes, such that it is having maximum distance from both the classes, but also having minimum misclassification error. And one of the excellent mathematical technique to do that is, of course, the support vector machines, SVM, which chooses hyperplane that way. Okay, so having discussed all these things, essentially, I think I touched upon in different segments. This is actually the overall machine learning ambit, if you have to understand. So there is a classification group, and this group is, I will call that as a supervised group, and it includes, of course, the classification and regression. So that fitting of hyperplane can be considered as a regression problem as well. And the other unsupervised group is, of course, the clustering, the density estimation. We have seen that DB-scan kind of algorithms. And we have also discussed dimensionality reduction a little bit. Remember that principal component analysis problem, where we brought down a high dimensional feature space to lower dimensional manageable space. And that actually covers sort of, encompasses the kind of machine learning ambit that we should look at. In fact, it looks like a complete one semester course here, but just to give you a brief idea on different segments, I think so far that's what I tried to touch upon. Any question? Okay, so I'll now go into the different applications with these introduction. I'll quickly scan through few applications that we have done and we are doing. Any questions so far? I think.
Please carry on, sir.
Yeah, I have around 10 minutes, right?
Yes, sir.
Okay. Okay, let's scan through the applications. This is one of the earliest application we did. This is on your left hand side. These are pad and paws of tiger. So this is a pad. The bigger piece segment is the pad, whereas you can see the fingertips. And the question was, by looking at these pad and paws, can you count the number of tigers? So what? So essentially, it means that if I have these two pictures, on your right hand side you have these black marks, black outlines. I mean, we work with these black outlines. If I give you two such sets, can you differentiate between these two sets? Now, how do you get this black outlines is different. It's in sort of a hack. It's like you put, and these are real data that we collected from Sundarban Tiger Reserve. So you can actually put plaster of Paris on these pad and paw on the ground, and then the mold, the Paris mold gets solidified, and then you bring that mold back to the lab, and on a white piece of paper, take a pencil and draw the outline of the pad and paw, and that's how you get these black borders. Now, given these, can you tell me how can we differentiate between two such sets of pad and pause? Any volunteer?
Maybe the distance between the centroid of that paw
Exactly.
and the
Exactly.
fingertips.
Yeah.
Maybe some will be smaller, maybe someone will be larger.
Okay. So let's say I collect 1,000 such data. So 1,000 such black outlines are there. Then what should I do?
For each one, a feature vector needs to be created.
Correct. And that feature vector will be, multidimensional. It has the
Yes.
area of those small circles, or area of the bigger pad, then the distance between the centroids, then the orientations of the centroid of these pieces, etc., etc. And you will have thousands such feature vectors, right?
Yes, sir.
And then you do what? To count the number of unique tigers, what you should do? On those 1,000 data points, find out the number of unique clusters, isn't it? So if I collect the data, if I collect the data at, say, morning 9 a.m., I collect the first data at morning 9 a.m., and my next data I collect maybe, half kilometer away at 9:30 a.m., then maybe the same tiger has traveled that that portion, and you collected the pad and paw of the same tiger, right?
Yes. Yes.
Maybe you
Then we
collected
can.
that, yeah, maybe you collected the data on Monday and you collect the data on Wednesday of the same tiger. So you have those samples with you, which are feature vectors, n-dimensional feature vectors, 1,000 such data points, find out the unique number of clusters, and those are possible counts of the tiger from the data set that you have, right? Yes, any question?
Sir, what about the soil condition? How do you expect that you'll have identical, say, for clustering?
Well, if the question is not the soil condition here, I'm assuming, well, there will be variations. So there will be distributions. I have shown you the Mahalanobis distance to take care of that. So of course, the same tiger, because of the soil condition, have a different kind of a little bit variations in the area, little bit variations in the orientation. And so let's look at the distribution then. And while finding out the clusters, we will not be using the Euclidean distance. We will look at the distribution and then select appropriate distances.
Okay, agreed.
So in absence of any other alternative, you have some feasible sort of mathematical solutions to the problem. Okay, actually we worked with this problem for long 3 years. That's a long story, but we come up with a number even estimated, which is very less compared to what the government predicts. And of course, government was very angry with us, even though our project was funded by UNDP, because UNDP wanted to cross-check the government's number, because UNDP funds these tiger reserves. And government was very angry with us because we could mathematically show that your figure doesn't match with our figure. And these are also biologically substantiated, because if you just say I have 400 tigers and there is not enough food for 400 tigers, then everyone will have a question mark on those numbers. Anyway, but that's not the point here. The point is there could be viable mathematical techniques, statistical techniques, to estimate such feature distributions. We did a problem with a crazy doctor, and the crazy doctor actually, so there in the old Ayurveda and even in Chinese medicines, there are maps available of the tongue, and the recording in those old scriptures are as if that if you have a particular color and texture in a part of a tongue, then you have certain ailments, certain diseases. And in earlier days, and even now, doctors, the first thing doctors probably do will want to see the tongue. So if you look at the map below on the screen, so you'll see a region of the tongue where the kidney signatures will be there. In the center, spleen and stomach signatures will be there. So by looking at the color, by looking at the texture in such regions, you should be able to predict the kind of diseases or ailments. Is the problem understandable?
Yes, sir.
Yeah. So our responsibility was to get this tongue image and then create a similar map and hand over the map to the doctor, and then the doctor is going to take a decision on that. We could successfully generate the map, but the project failed after that. That's a different story. But here is how we do that. We generate the segments of the tongue. See the top right hand side, and now you know how can we reach to this white segment against the black background. What you can do that? What is this process called? What is this process called?
Segmentation.
Segmentation, yes. I think after this 1.5 hours of class, at least we could understand that this is segmentation. That's good. And we can apply that kind of histogram techniques or k-means or fuzzy c-means. But the problem is easier here because we know that there are two classes. We want the tongue and the no tongue region. So just take two clusters and divide them into two parts. And here is how you're going to get the white tongue portion. And once you get these, find out the centroid, find out the circle, find out the tangent, and you get a map similar to the map that is available in the Chinese medicine or the Ayurveda, old Ayurveda scriptures. Now, once you have these regions, I mean you have 1, 2, 3, 4, 5 regions, then you calculate different features of these regions and tell the doctors that here is the feature of the kidney region. But there comes the failure of the project. See, the way the doctors are trained and the features that we calculate are different. So doctors are trained that if it is a pale yellow, if it is a light blue, if there is a some shades on the tongue, then such and such disease. But it is difficult for us to actually come up with a mathematical number which represents what the doctors are actually thinking. So there is a gap, there is a feature gap. And this feature gap is essentially an art. You have mathematics at your disposal, but you exactly don't know what kind of combinations of feature that you have to do, you have to find out, so that you get the correct appreciation of a medical doctor, right? So there is that missing link that we could not establish, but otherwise geometrically we could get the tongue and get the regions just like the scriptures actually says, very similar to that. Any question?
You may carry on, sir.
Yeah. Okay. This is a iron. This is a coal ore segmentation problem, and this problem is very. It's not much common to Indian scenario, but well, see on the top left hand side you will see those ores. These are actually rocks, hard rocks, and the rocks are actually transported in a conveyor belt. It is going to a mine. Well, sorry, it's coming from a mine and going to a crusher. So crusher means it's going to crush it and then actually form a slurry, and from the slurry oil is actually taken out. So the question here is, can these size of the rocks be measured? So so this is a video input. This video of these of the rocks are coming out. Then can you find out the size of the rocks? Because from the size of the rocks, you can estimate what would be the slurry, what would be the amount of slurry that you can form. And if you see the image just bottom of that, you will see that large colorful pieces. That's the output of the segmentation. We could segment the pieces, and these pieces, by looking at these pieces, you can find out the area of these segments, and then you can have a distribution of these pieces. And you can actually draw the histogram of these histogram of the size of those pieces. On the right hand side, you see a histogram, and these x-axis 40, 60, 80, 100. These all represents in millimeter. So 40 millimeter size rock, 60 millimeter size rock, 80 millimeter size rock, and this is how you look at the histogram. This is actually a live project. We could achieve as close as 70% accuracy, but in absence of any other measure where you don't have any estimate of what would be the rock size, this gives you sort of 70 to 75% accuracy, even in a hostile environment. Okay, so there is this is an sorry, the video is probably not working, but we have developed this Anubhav app where we could actually find out the emotions in the real time, and so whether this is our student Bikash, and as he will make different emotions, since I'm sorry that the video is somehow not working, you could actually say whether it's surprise. There are actually 6 basic emotions, disgust, surprise, sorrow, happiness, and whether you could predict or recognize the emotions of this person. So this was actually funded by Qualcomm in the process. Anyway, I think let me stop it here. And there are many applications. I think I shared the handouts. You can have a look at the handouts. Send me an email if you have any questions.
Sir, can you speak few things about that last medical tracking surgical tools?
Oh, surgical tools. Again, I think the video is not going to work probably. The surgical tools tracking problem is a very interesting problem. So during a medical operation, there are devices now to actually track. Actually, none of my video is working for some reason. I don't know why. I don't know why it's not working. But sorry. Yeah. So it's kind of a medical records there they keep. So how the tools are used, and what purpose these particular tools are used. These are recorded for medico-legal reasons, and also to explore what are the uses of different devices. So what you need to do is you need to track those devices. What happens? The surgeon's hand is going to be moving, and as the hands are moving, you tag the hand and you track the devices along the fixed with the hand, and you can do that both internally and externally. So this is external, using the external camera as the operation is going on, and this is internal camera as the as internally how the the device will come inside and will be doing some operations inside. So that operations can be done alongside. So you track internally, track externally. The major challenge that we could not do is to synchronize the internal and external data. That's very difficult, and we don't have enough data. In fact, there is some privacy issue, and the company is one of the major company from Canada actually funded this project, but then at a later point they actually withdrew from this project. So they don't want to continue because for I don't know, for other reasons. So we could not complete the project, but we only have very few data sets, and we do not also have the permission to publish these information, these results. So we do not have any publication also of this particular. Okay. Yeah. Any more question?
Any questions from any of the?
I'm sorry, I could not cover most of them because I think I was a little bit slow, and there is a reason to do because we need to understand what is happening.
Yeah, this one also was interesting. Leukocyte tracking.
Yeah, this is leukocyte tracking, and these are used for drug target studies. So these are not allowed on human beings. These are allowed on the animal, right? So these are mouse. So mouse is actually injected with a virus, and then the mouse is injected with a medicine. Under the influence of the medicine, doctors want to track how the leukocytes flow, because the leukocytes are fighting against those germs or viruses or whatever. So tracking leukocytes under the influence of a drug, and these are used for drug comparing study. So under the influence of drug A and under the influence of drug B, how the leukocytes perform, rolling. So that data is being tracked. Okay.
So how these images are captured actually? Leukocyte tracking, whatever image you have shown.
This is an optical microscope images. This is a very painful process for the mouse. So the thigh muscle of the mouse is exposed, right? And this in a clip, the mouse is clamped against a flat table. Then so mouse is fixed. Mouse thigh muscles is exposed under a microscope, and you take an emery paper, rub the emery paper on the muscle, so that the hair and the skin becomes little bit clear, and then you start taking picture. You cannot kill the mouse. If you kill the mouse, then blood flow will stop. So, and that is how you collect the data through an optical microscope against the optical lights. This is a very standard procedure for drug targeting studies. Our work is to support that biomedical teams. Okay. Good.
Any more queries?
Sir, any some recent topics on which we can work on? Recent research issues.
They are all. I give you certain questions. Yeah. So maybe there are see these are different applications. Soccer analytics, you can actually we are working currently on this problem. You can work on that. So we are calculating the possession statistics. So team A, team B, what percentage of time ball is with team A, what percentage of time with ball with team B. Can you calculate automatically? We are working on this project. There are many areas. Is there any goal? Can you detect the goal automatically? Is there any foul? Is the ball going out of play? Can you find that automatically from the video? That's a good area. These are industrial problems, and we get funded projects. These are Tata Steel projects that we get. This is an important problem. This is funded by TCS. So on the supermarkets, you see these stacks of products. But you take an image and find out which product is where. Where is Kellogg's cornflakes? Where is Britannia biscuit? There is an interesting commercial aspect to this kind of problem. So many interesting problems. You see, you look around, there is a huge number of problems, and yeah. So we have patents on these problems. We have actually working systems on this problem with in TCS product line. So you know, just look around, you'll find the problems. Many interesting applications, lots of benchmark data. Look at the medical imaging problem. If you are interested in PhD, look for the good conferences. You know, conferences like CVPR, conferences like ICCV, conferences like MICCAI, MICCAI, and look at the challenges. So all these conferences publish challenges. They give data and they give the challenging problem. So pick up those challenges as your research topic. That's a very good area to start with. And I always advise students to follow that kind of path.
One more thing, any source for that you have discussed about distance and the distribution,
Distance and uh,
distance calculation and the distribution. Any source from which we can
oh,
study? Actually,
there are
I
many.
always, I
You look
always,
at
I've applied it, but randomly actually. Wherever I got good result, I
yeah,
used it, but could not explain it why I use such distance measure.
yeah. Well, there are many. I mean, you pick up any textbook on I don't know any on basic textbook on pattern recognition, and you should be able to get statistical pattern recognition or computer vision textbooks. Look at the internet resources. CV Online, capital C, capital V, online. CV Online. That's a very good resource for computer vision and related work. Search by Mohammad's distance. Search by distance metric. So you should be able to explore different such areas.
But actually, they never mention about the reason. They give some distance measure, it's okay. We use that formula to evaluate, but
Yeah,
the
that's
reason actually I
see,
could not find.
yeah,
Concrete reason I could not find.
I understand that. Yeah. Hopefully, you could
Okay,
understand 1% or 2% of what I said.
yes,
But
yes, sir, yes. Okay, sir, thank you.
yeah,
Okay, sir.
yeah,
So I
yeah,
really appreciate your presentation.
yeah. Thank you.
The way you explained from simple concepts.
Sorry that I could not go much further because of the pace, but I think that's fine. Yeah,
Yeah, I understand that due to the limitation of time and also we have back-to-back sessions. So
yeah,
there are
right.
some other restrictions.
Yeah, sure.
So thank you very much. Looking
Thank you.
forward
Thank you.
to have
Yeah.
more conversations with you in future.
Okay. Thank you.
Okay, thank you. Yeah.
Thanks very much. I'm just logging off then. Okay.
Sure, sir.
Yeah. Bye.
Okay, all the participants. So let us take a break. So after 15 minutes again, we'll be here to have the second session of day 5. Thank you all of you. Any queries from anybody?